If you follow nanotechnology, you already know the ultimate challenge isn't just building things atom by atom. It's actually proving you did it right. I mean, how do you definitively know you've engineered the perfect surface chemistry when you're operating completely in the dark, way beyond what any microscope can see? Well, that is where our nanoscale detective comes in, Fourier Transform Infrared Spectroscopy, or just FTIR for short. Okay, let's dive into this and uncover exactly how we decode the invisible.
Real quick, here is our roadmap for today's explainer. 1. The nanoscale detective. 2. How FTIR spectroscopy works. 3. Modifying and building nanomaterials. 4. Green tech and nanomedicine. And finally, 5. The advantages of FTIR.
Section 1. The nanoscale detective, solving the invisible mystery.
It brings up this really profound question, right? How do we analyze something we literally can't even see? Say you're attaching a specific targeting ligand to a gold nanoparticle for a new cancer treatment. A standard microscope is totally useless here. You need to go way beyond just looking at the shape of it. You need to know the exact chemical composition and how things are bonding at the surface. Basically, you need the molecular fingerprint.
And this brilliantly illustrates the entire solution. This is our master roadmap for the explainer, a complete breakdown of FTIR spectroscopy and nanotechnology. It captures everything from the core physics of infrared absorbance at the top, down through the real-world applications in synthesis and nanomedicine, all the way to the key analytical advantages. We're going to unpack this whole thing piece by piece. Section 2. How FTIR spectroscopy works. Decoding the molecular fingerprint.
Let's trace how this actually works. It starts with a broadband infrared radiation source. That beam shoots into what's called a Michelson interferometer, which splits and recombines the light to create an interference pattern. When this beam hits our tiny sample, specific infrared frequencies get absorbed, and those frequencies correspond directly to the physical vibrations of the chemical bonds inside. Finally, a detector catches the light that makes it through, and some very clever Fourier Transform math decodes that messy signal into a clean, readable spectrum, plotting absorbance against wave number.
Now, that raw, messy output straight from the interferometer, that's called the interferogram. To the human eye, it's just a jumbled wave of noise in the time domain. The real brilliance of the system is that Fourier Transform math, which translates that messy time domain signal into the frequency domain, extracting the usable spectrum we actually analyze.
Once that mat does its thing, boom, we get our molecular fingerprint. Every peak tells a story. An OH stretch is always going to show up between 3,200 and 3,600 inverse centimeters. A carbonyl group, carbon double bonded to oxygen, hits right around 1680. CO single bonds sit at 1100, while metal-oxygen bonds drop down into the fingerprint region below 700. Map these out and you know exactly what is on the surface of your material.
Section 3. Modifying and building nanomaterials, surface chemistry, and nanocomposites.
Now, what's really interesting about this is that when we engineer nanoparticles, leaving the surface bare is almost never the goal. We coat them with capping agents, ligands, or polymers to make them stable or give them specific jobs. FTIR acts as the ultimate truth teller here. If you see the signature peaks of your polymer showing up on the nanoparticle spectrum, it proves without a doubt that it's successfully attached, covalently attached, not just loosely stuck there. On the flip side, if you see unexpected peaks, it immediately flags impurities left over from your synthesis.
FTIR is just as critical when we are mixing things up to form nanocomposites. But here, beyond just finding functional groups, we are hunting for peak shifts. If a nanoparticle forms a bond, like a hydrogen bond with the surrounding polymer matrix, it literally alters how that bond vibrates. So, on our graph, the peak shifts just a tiny bit left or right compared to the pure polymer. That subtle little shift, that is concrete evidence of strong interfacial bonding, proving you have a solid composite, rather than things just separating out.
So it's an absolutely indispensable tool for structural materials. But the true cutting edge of FTIR application really lies in how it's pushing forward health and sustainability.
Section 4. Green tech and nanomedicine, eco-friendly synthesis and targeted drug delivery.
Traditionally, synthesizing nanoparticles means using some pretty harsh, toxic chemicals. But there's this massive shift toward green synthesis now. We're using plant extracts full of phytochemicals like phenols and flavonoids to safely reduce and stabilize the metals. FTIR is absolutely essential for validating this. By comparing the raw plant extract to our synthesized nanoparticle, we can watch specific peaks disappear or shift. It pinpoints exactly which biomolecules did the heavy lifting, which means we get our nanomaterials with significantly less toxic waste for our planet.
So, the crucial point in nanomedicine is encapsulation. When you build a tiny polymer carrier to deliver drugs straight to a tumor, you have to prove the drug is actually tucked safely inside. You start with a blank nanoparticle for your baseline spectrum, then you scan the loaded carrier. The emergence of the drug signature peaks inside the carrier spectrum proves successful loading. Plus, analyzing those peak shifts tells us if the drug and the carrier are chemically compatible, ensuring the payload stays secure until it hits its target.
Section 5. The advantages of FTIR. Why it's the ultimate analytical tool.
Let's do a rapid-fire summary of the actionable intel this tool actually gathers. FTIR definitively identifies functional groups and maps out surface chemistry. It validates molecular interactions and bonding states. It lets you monitor chemical reactions in real time and acts as a stringent test for material purity. Basically, it tells you exactly what is present and, crucially, what is absent.
Beyond the data itself, the operational perks are seriously hard to beat. The technique is completely non-destructive, preserving your valuable samples. Analysis is incredibly rapid. You get a full spectrum in literally seconds. It offers high sensitivity for trace detection, requires barely any sample prep, and ultimately, it is just a highly versatile, completely reliable workhorse for almost any nanomaterial system.
By serving as our eyes in this invisible world of molecular vibrations, FTIR guarantees that when we engineer materials atom by atom, we know exactly what we've built. But the applications we covered today, that's really just the foundation. As nanotechnology continues to build our future one atom at a time, what invisible mysteries will FTIR solve next? Thanks for joining me for this explainer. Keep exploring.